Respect fellow experts, ladies and gentlemen, everybody is fine. It's an honor to attend the 2021 American Control Conference. My name is Qiufeng Wang, and my supervisor is Professor Zhengqiang Zhang. We are from the School of Engineering of Qufu Normal University, China. Today, the topic of my presentation is globally stable adaptive neural network control for uncertain output feedback systems. My speech is divided into the following 6 parts. The first part is introduction. The second part is preliminary results. The third part is system description and state of the real design. The fourth part is adaptive neural network control design. The fifth part is simulation results, and the last part is conclusion. Firstly, the introduction. The adaptive control methods based on approximation for nonlinear systems with high uncertainty have been extensively studied. Almost all adaptive neural network control schemes can only achieve the semi-global stability of the control systems because the approximation ability of neural network is only effective in the approximation domain. For uncertain output feedback systems, there is no research achievement to realize the global control problem based on neural network approximation. The major technical contributions. The number one switching function is constructed to achieve the smooth switching between the adaptive neural network controller and the robust controller. The number two, the adaptive neural network control stutter and backstepping technique are combined to ensure that all signals of closed-loop system are globally uniformly ultimately bounded. In the preliminary results, we designed a switching function my with the following form, where R1 and R2 as the switching lower bound and the switching upper bound of y, which satisfies this. Then we give the system description. Consider the following second-order output feedback nonlinear system, where x, y, u are the system state vector, output signal, and control input respectively. B0 is a known constant gain. F, I, y are unknown smooth functions. Phi I are known smooth functions. Di are bounded time varying disturbance signals. Only the output signal y can be measured. Our control objective is to design a controller U such that the closed-loop system is globally uniformly ultimately bounded. To achieve this objective, we give the following two assumptions. Assumption 1. Suppose that there exists some known K-class functions beta such that. Assumption 2. Suppose that there exists some unknown positive constant Di such that. Using radial basis functions, neural networks to approximate the unknown function Fi. Therefore, the system can be rewritten as this. Then we give the state of the view as this. Define the state estimation error as this, and parameter estimation error as this. Then we can get the dynamics of state estimation error as this, where A0 is always and there exists a positive definite matrix P such that the next part is adaptive neural network control design. Firstly, design coordinate transformation as this. Z1 is equal to y minus yr. Z2 is equal to hat x2 minus alpha 1, where alpha 1 is stabilizing function to be designed. Step 1. The dynamics of tracking error Z1 is as follows. Then we choose the first Lyapunov function as this. According to the above Lyapunov function, we can design the virtual control alpha 1 as this, where alpha 1n is the adaptive neural network controller working in the approximation domain, and the alpha 1r is the extra robust controller working outside the approximation domain. The first set of tuning functions are chosen as this, and the adaptive law of this parameter is chosen as this. Step 2. The dynamics of the second coordinate transformation Z2 is this. Then we consider the second Lyapunov function candidate V2 as this. From the second Lyapunov function, we can design the controller U as this. Where alpha 2n and alpha 1 2n are the adaptive neural network controllers working in the approximation domain, and alpha 2r and alpha 1 2r are the robust controllers working outside the approximation domain. Design the adaptive laws of the second set of parameters as this. According to the second set of tuning functions, we can give the adaptive laws of the first set of parameters as this. Last, we can give the mean result. For the uncertain output feedback nonlinear system, we design the state observer, the control law, and the adaptive laws. If the following design parameters are chosen such that the following three conditions hold, then all the signals are globally bounded all the time, and the output tracking error converges to the small neighborhood. In order to verify the effectiveness of the proposed control method, we give one simulation example. Consider the following second-order differential equation. where b0 is equal to 10. f1 and f2 are the functions assumed to be unknown. Phi1 and Phi2 are the known functions. D1 and D2 are the bounded time varying disturbance signals, and the reference output is taken as this. The known functions are selected as this. Figure 1 shows the trajectories of system states x1, x2, and the reference signal yr, and the trajectories of tracking error z1. Figure 2 shows the trajectories of the first set of parameters. Figure 3 shows the trajectories of the second set of parameters. 4 shows the trajectories of switching function my and the controller u. The last part is conclusion. The algorithm pledges that all variables are globally uniformly ultimately bounded, as well as tracking error converges to a small neighborhood. The tracking error reached to the predetermined tracking accuracy needs to be further studied. This is the next research direction. Thank you for your attention.